So we will continue today the chapter on internal forces. Okay. We have seen last time that internal forces in 2D can be divided into shear forces and normal force and the bending moments. Okay. Now in this part of the course, we will learn how to find the variation of the shear along a structure. Okay, variation of shear, normal force, and bending moment along a structure. So first, we will see that if we have a distributed load, what will happen? Okay, to understand what will happen if we have a distributed load on the structure, let us take a very small element. So here, as you can see in this figure, you have a beam subjected to forces, concentrated forces F1, F2, and to a distributed load on part AD, in addition to couples. Okay, so you have variable load on this system. Now, if I take a small part of it and I do the analysis on it, okay, we said that since the whole structure is in equilibrium, then also the small part will be in equilibrium. Okay, now what are my internal forces? Since I did a cut from two sides, so here from the first side, the convention is to have V in a way to rotate about the other extremity. So V should be upward, okay? And for the moment, the convention is that it should compress the upper part. So the couple moment will be like this, okay? From this side. So I will call the force at this level here, I will call it shear V, and I will call the moment M. And of course, since I am cutting at any location X, so as you can see here, I did the first cut I did it at a distance X. So the distance here from the beginning of the beam until my cut is X. Okay, and I have that for the second cut, I just took a very small element. This is why the distance here is very small, is delta X equal to, when it's 10 to 0, it's dx. Okay, so this distance here is dx. So now, next step, when I did my cut at the second level, the difference between the two cuts is a distance of dx. So this distance here is dx. Okay. And now on the other side, V and M will be different than on this one because it's a function. V and M will vary with location. Okay. So I will say that if I want to represent V and M, I have here at this level, V should be down to rotate clockwise about the end of the beam. And the couple should be counterclockwise to compress the upper part of the beam. Okay. And now I will say, since I have a variation dx in along the beam, so I can say that V is equal to V plus dV. Okay. And M is equal to M plus an elementary variation of df. Okay. Or if you want first, what we will do first, we will consider the distance delta x. So if you consider the distance is a certain delta x, then V is V plus delta V, and M is M plus delta M. Then we will tend delta to a very small value. So we tend delta x to dx, and we will see what relation we will obtain. Okay. Our purpose is to relate the shear to the distributed load. Okay. So what we will do first, if we want to find a relation between V and W, we can do sum of forces. If we take this element and we do sum of forces along y equals 0, what do we obtain? We have first we have plus V, which is up, so I put plus V. Okay. From the other side, I have V plus dV downward, so I put minus V plus delta V. Now I will look at my system. It is subjected to what? It is subjected on this small part to a distributed load. Okay, because look, I have taken a part where I
ما
only
شفت
a distributed load. So the force on it, you know that if I have a distributed load, I can calculate delta F because I have taken delta X very small. So delta F is simply the area of this part. Okay. And when you take a very small delta X, you can consider this is nearly a rectangle because W will not vary for a very small variation of X. So the force of distributed load here, if I consider an upward distributed load, it will be plus W delta X. And if I take a downward distributed load, it will be minus W delta. So now, if we replace back into this equation, what do you obtain? V and minus V will cancel out. You will obtain that delta V is equal to Wx delta X. Okay? And if I take dx tend to 0, I can write that dv is equal to omega x dx. This means that I can, if I take the x to the other side, what do I obtain? I obtain this relation, which is very important, which tell me that the variation in shear over the beam, dv by dx, is equal to wx, where wx represents the distributed load intensity, okay? And dv by dx represents the slope of the shear diagram. So what I can conclude from this information, for example, if I have a rectangular load, then W is constant. How will be V? Look, if you have W constant and negative, so downward. So what can you conclude? Let's say, for example, I gave you a force of W equal to 5 Newton per meter downward. So you can tell me that dV by dx is equal to minus 5, minus because here W is down. So what can I conclude? So V is varying in a linear way with respect to x, okay? So V as a function of x is linear, and it will be decreasing or increasing. It's a decreasing function or increasing function. dv by dx represents the slope, okay? The sign of the slope will tell you if it's increasing or decreasing. Since you have a negative slope, okay, it is decreasing. So, and v is decreasing because of negative slope, okay? So now, the other information that I can use in this case from this conclusion is that I can integrate, because you know, look, you have dv equal wx dx. If you integrate from each side, what do you get? You get that integral dv equal to integral omega x dx, okay? So the change in shear delta v is equal to integral omega dx, which represents the area under the curve. Okay, so if for example here I start from 0 to 2 meters, okay, I can say that the variation of shear between 0 and 2 is equal to the area of this part, okay? So if I give you the initial shear, let's say you know the initial shear is 0, then you can say that V, the shear at 2, is equal to this area, okay? 2 times 5 equal to 10. We will do a lot of examples on this, don't worry. Okay, now, the second step, we will continue to find relations for internal forces. Now we will deal with moment variation, okay? So if you take the same small element and you want to find how your moment is varying, you should do sum of moments equal to 0. So we choose here the small element, and we choose to do sum of moment about the point here, which is this is O. If you do sum of moment about O, what do you have? First, you should choose a positive direction. We choose the counterclockwise as positive, as you can see here. We mentioned that the counterclockwise direction is positive. And then we have plus m plus delta m. minus m. Now, since we choose to do sum of moment about O, V plus delta V will not have a moment, okay? But V here will have a moment, and its moment is clockwise, so it's a negative. So this is why we did minus V times the distance. The distance is delta x, so minus V delta x, okay? Now, for the distributed load, you know that when you have a distributed load, your resultant force should pass by the center of the area. So for the distributed load, I can replace it by a resultant force at a certain distance here. Okay. Now I don't know exactly what is the distance because it depends on the type of the distributed load. Now, if I consider that I have taken a very small element, k will be close to half, because you know that for a rectangle, it is just at the middle, okay? So here, if I assume that since the x is very small, I can take it at the middle of this small part, then the distance here will be nearly delta x over 2, okay? Anyway, whatever is the distance, whatever is k, you will see that it will not affect the result, and we will see why. Because here, when I want to find the moment of the force, I will do the force, which is wx delta x, and it's minus, because it's turning in the clockwise direction. So minus the force times the distance, you get wx delta x times k delta x, and then it is plus k wx delta x squared. So as you can see here, the moment of the distributed load is proportional to delta x squared, which is much smaller compared to delta x. Can you please mute your microphone, guys? Guys, please mute your microphones when you don't ask questions. Do you hear me? Please mute your microphone when you don't ask questions. So here, if you take delta x tending to 0, okay, you will see that this term is negligible compared to this one. So because it's proportional to delta x squared, okay? So you can say that I can neglect this term compared to this one. And then I deduce that delta m is equal to v delta x. And now, if I replace by tending delta x to 0, I replace delta x by dx. I get that dm over dx is equal to v. And from here, I deduce that the slope of the moment diagram is equal to the shear. Okay? Now, if I integrate this relation, as I did in the previous slide, I obtain that the change in moment, delta m, is equal to integral v dx, which is the area under the shear diagram. Okay, and we will see how we will use these relations in problems to know how the shear and bending moment are varying along the structure. Any question until here? Okay, now next step, you know that you might encounter in calculation several types of loading. You can have distributed load, you can have constant forces, okay, or located forces located at concentrated at one point. So before we have seen the effect of a distributed load. Now we will see the effect of a concentrated force. So I will take a small element, including a force, a concentrated force at a point, and I want to see how F will affect my shear variation. Okay, so as usual, I take the element, I put Vm at the two sides, and I do sum of forces equal 0 on this element. If I do here sum of forces equal 0, what do I get? I get V plus F minus V plus delta V equals to 0. So I deduce that for the concentrated force, delta V is equal to F. This means what? That the variation of shear, when I have a force, I have a jump in the shear, and the jump in the shear is equal to the value of the force. So if you have an upward force on your system, the shear will do an upward jump, and if you have a negative force acting on your beam or structure, you will have the shear will have a negative jump. And we will see how to use this information in drawing shear diagram. Now, another possible type of loading is concentrated moment. Just before moving to the concentrated moment, you should pay attention. The concentrated force will affect the shear, okay, but will not affect the moment. So the moment will remain the same. You know why? Because if you try here to do the analysis for the moment, you have here the distance is very small. It's k delta x, okay? This distance is k times delta dx. Or delta x.
Over 2 coming.
So if you do sum of moments, what do you get? Let's say we have choose the counterclockwise as positive. You obtain m plus delta m, okay, plus delta m, and minus v times delta x, and minus m, and minus f, which is, I will replace f by, no, here if you want, it's just f times the distance. The distance is k times delta of x equals to 0, okay? So now, as you can deduce, when you do your calculation, here the distance, we have that v delta x and k delta x are very small compared to v. And if you put like this, if you simplify m, you will obtain this. You simplify m here, m minus m, okay? You get that delta m is simply equal to v plus f k times delta x, okay? Now, if you take delta x in your problem, you are always taking a very small element. So delta x tends to 0, okay? So since delta x tends to 0, this term tends to 0, then you can say that, well, what will be delta m due to a concentrated force? Delta m due to concentrated force is 0. So the moment will not change due to the effect of a concentrated force. The moment will only change due to the effect of a concentrated moment. So if I give you here, okay, here if you have a concentrated couple on your structure, let's say you have a clockwise couple M0, and you want to see its effect on, of course, first for the shear, it will not affect the shear. Okay, so the shear will remain, the value of the shear will remain the same, because the shear is affected when you do sum of y equals 0. The couple will not enter into sum of y equals 0. The couple M0 will enter in sum of moments equals 0. So if you write sum of moments equals 0 to this system, you get that m plus delta m minus m0 equals to 0. So you deduce that delta m is equal to the couple m0, okay? And you can deduce that if I have a clockwise moment, I have an upward jump of the bending moment. And if I have a counterclockwise moment, the bending moment will jump down. Okay? Now, to understand more all of these issues, we will do some examples together. Let us start by this example. The support reactions, no, just let me see the given. So you have draw the shear and moment diagrams for the following beam. Let me zoom it out a little bit. Okay, so here I want to draw shear and bending moment for this beam. So I want to draw how V is varying and how moment is varying. Now, if you remember, as we have seen last time together, in general, before starting, I should calculate the reactions. Here, what do I have here? I have a fixity. Okay, for the fixity, the reactions are Bx, By, and a couple. Okay, but you know what? Now there is no need to start by calculation of the reaction at the fixity because I can start from A to B. Okay, so if I start from A to B, I no need to find the reactions. But we will see together that if you calculate the reaction, you can use them as verification for your results. You will see how. Okay, now let us start together step by step. First, at A, what do I have at A? At A, I have a downward force, a downward concentrated force of 2 kilonewton. So for the shear, you know that what is the effect of a concentrated force on the shear? It will cause me a downward jump. So initially, this is my V variation, okay? Let me zoom it more.
بس يا جماعة بيحكي فيه يعمل ميوت بليز.
Please mute when you don't ask questions. ما بدها هالقد. Okay. So now here, okay, initially this is at the start of my beam. Initially I start from just before of my beam, I don't have anything, it's zero. Okay, now when I started my beam, I have a downward force of 2 kilonewton. The downward force, as we have seen together, will cause a downward jump of the shear. So I will directly start by a downward jump of 2. So the value of shear at the initial point is -2. Now, in this part of my beam, do I have any load? I don't have any load here. When you don't have any load on your beam, the shear will not change, because shear can change or due to concentrated force or due to distributed load. But since I don't have any type of loading on this part, then my shear will remain constant. So it will remain constant until I start by the distributed load. Okay? Now, when I start by the distributed load, what will happen? We have seen together that we have the following property, that dV by dx is equal to W. This means what? This means that W represents the slope of V. Okay? Now, since in this part W is a constant, W is equal to what here? It's a constant negative because the distributed load is downward. So I can say that for this part, W is equal to minus 1.5. Okay? This is why I have a linear variation of my shear, and the linear variation is characterized by a slope of minus 1.5. So I can put here near the figure slope equals to minus 1.5. Now, if I want to know what is my final result, what is my final shear, I can use which property? I can use the following property, that delta of V is equal to integral omega dx, or what? Which correspond to what? Area under curve. Okay, so here, since it's a negative W, then I will consider a negative result. So I will take minus the area if you want. Okay, so here I should take minus the area because my W is downward, and the area under the distributed load is what? It is this distance, which is 2 times 1.5. So I can say that delta V is equal to minus 3. Okay, now what is delta V? Delta V is the shear at the final point after the distributed load will finish. So the distributed load is finishing at this point and it's beginning at this point. So I should do delta V between let's say V at 4 meters and V at 2 meters. Okay, so I can write now V at 4 meters minus V at 2 meters is equal to the minus the area, so it's minus 3. Okay, and now I know that V2 is equal to what? It's minus 2. So I deduce that V at 4 is equal to minus 3 plus V2 equals to minus 5. Okay, because I have minus 3 minus 2 equals to minus 5. Okay, and now I am done with my diagram for shear. Okay, I will give you a hint how you can verify your result. You can verify your result by calculating By. You know why you can do this? Because look, when your beam will finish, directly after your beam, the shear will be what? Will be 0, because your beam is in equilibrium. So if you do a cut just after the beam, you don't have anything. So sum of forces on the other part should be equal to 0. This is why we say that the value of By, the value of the reaction at B, should bring back my shear to 0. It should bring back my shear to 0. So I can say that I can predict that the value of By should be 5. Okay, because we need 5 to go back to 0. So to make sure of this, let us calculate By together. If you want to calculate the reaction By, what should we do? We should do sum of forces along Y for the beam equals to 0. So if I do for this beam sum of Y equals to 0, what do I get? I have minus 2 minus the area of the distributed load, which is minus 2 times 1.5, plus By equals to 0. So By is equal to 5, and I can verify my result. Okay, now the second step, I want to draw the moment diagram. They ask for the moment diagram. So for the moment diagram, you should always look at two things. You should look at your beam to see if you have couples, and you should look at your shear, because the shear is the derivative of bending moment. Okay, now why I told you should also look at your beam, because if you have couples, okay, the couples, you cannot see them in the shear diagram. And for the shear diagram, you cannot know if I have couples or not. You should always look at your force, your diagram of loading to know if I have couples, because if I have couples, I will have jump in moment. Okay, and from the other hand, I will look at V, because V represents the slope of variation of my moment diagram. Okay, so now let us see how to draw the moment diagram. First, as the first step, at the beginning of my beam, okay, do I have a couple here? No. So I will start my moment will start by 0. The only way to not start by 0 is to have a couple here. If I have a couple here, then I will start by a jump. If my couple is clockwise, I have a positive jump, so I start by a positive value. If my couple is counterclockwise, it's a negative value. Okay, now I can have a couple, or the second possibility, if I have a fixity, because if I have a fixity, I will have a reaction moment, and then I will have the bending moment will not start by 0. Okay, so now, since I don't have anything, any couple, any fixity here, I will start my bending moment by 0. So for my starting point, I will start from 0. Next step, since I know now my starting point, which is here, I will look at V diagram. Okay, for my V diagram, what do I have? For the first step, V is constant negative. It's equal to minus 2. And I know that the shear is the slope of moment, because we have derived together that dm by dx is equal to what? is equal to the shear. This means that if the shear is constant, M will be linear, okay? And if the shear is negative, M will be decreasing. This is why here I can say, since V constant negative, I have M linear decreasing. It will decrease in a linear way, and I can write here that the slope of decrease, the slope is equal to -2, which is the value of the shear. Now, to know how much it will decrease, okay, we do the same procedure we did for the previous case. Okay, we say that we have that the delta M, okay, delta M, the variation of moment between these 2 points, is equal to the moment at point 2 minus the moment at x equals 0. It is equal to what? To the area under the curve. But here, since it's a negative value for V, so I will take, so my area is below the axis, I will take a negative value, so it's minus this area. Okay, this area is what? 2 times 2, because it's a rectangle. So I do minus, it's equal to -2 times 2 equals to -4, okay? And since initially M0 is 0, so I deduce that the bending moment at point x equal 2 is equal to -4, okay? So now I know this value here. Okay, this value at this point is -4. So now, the next step, I will continue my diagram. In the next step, the shear becomes linear. Linear, decreasing. When your shear is linear, your moment will be a second degree parabola. Okay? Why? Because we said that the derivative of M is V. So if V is constant, M is linear. If V is linear, M is second degree. If V is second degree, M is third degree. Okay? So I have a parabola here. It's a parabolic shape, second degree parabola. Now, to know how to draw my parabola, I look at the slope. Okay? So first look, at the start of my parabola, what was the value of V? You look here. V here is -2. So I should start by a slope. At this level, the slope is -2. And what is happening for my slope? My slope is increasing in the negative direction. So if you want, I can, it's becoming steeper. And my final slope at the final point, to know my slope at the final point, I just read the value of V here, which is -5. So what I can put here, I put that I have here at this point at the beginning slope equals to -2. And at the end point, I have a slope s equals to -5. Okay? Since your slope, from your slope variation, you can deduce the form of your parabola, the concavity of your parabola. So here it's clear that your parabola is concave downward. Okay? It's concave downward. So like this. And you know what? Also, you can directly know that it's concave downward by doing another result. You have here that the derivative of m by dx is v. And you know that the derivative of v by dx is what? Is w. Okay? So if I replace here v by dm by dx, I deduce that the second derivative of m with respect to x, okay, is equal to what? To w. And the second derivative will give you an idea about the concavity. You know that if the second derivative is positive, you can say that concavity is upward. Concavity is upward. And if it is negative, then your concavity is downward. And in this problem, W was negative. This is why you can predict that the concavity will be downward. Okay. And now, still, we should find one thing to finish. We should find at which point the moment diagram will end. So what is the end value of the moment? To find the end value of the moment, I say that the moment variation between 2 and 4 is equal to what? Is equal to the area of this part. This is a trapezoid. So to find its area, I can divide it or into two parts, or I can use a rule that the area of a trapezoid is given by what? It's given by this base, okay, times this height over 2. Okay, this is another method if you want. So we can say that the area of the trapezoid, so let us write it here. The area of trapezoid is equal to the small base is equal to 2 plus the big base is equal to 3. Sorry, to 5. To 5. So 2 plus 5 times the height. The height is equal to 2 over 2, which will give me equal to 7. So the area of this part is 7. You can also divide it into rectangle and triangle, and you find that it's equal to 7. But since it is below x-axis, so I will take the negative area. So I can say that delta m between 2 and 4, okay? So delta m between 2 and 4 meters is equal to m at 4, moment at 4 meters minus moment at 2 meters equals to minus 7. Okay, and we have already calculated that the moment at 2 is minus 4. So I deduce that moment at 4 meters is equal to m2 minus 7, which is equal to minus 4 minus 7 equals to minus 11. Okay, so as you can see here, we obtained the value which is minus 11. Now, also, another way to verify your result, as we did for the shear, okay? Here we have a fixity at the end. This is why we expect that we will not end by a moment of 0. If you don't have a fixity at the end, or you don't have a couple at the end, then you should end by 0. Now, how to make sure of our value? We say that the couple at the fixity should be in a way to bring my value to 0. Okay, so to bring my value to 0, I should have an upward jump. This means I should have a couple in the clockwise direction, and my couple m0 should be equal to, so m at fixity, couple at fixity, should be equal to plus 11, of course, in the clockwise. Let us verify this together. Okay, to verify this, we will go back to the beam. Okay, let us say that I want to calculate the couple, the clockwise couple at the fixity. To calculate this couple, I can do sum of moments about b equals to 0. So if I do sum of moments about b equals to 0, and I take the clockwise as positive, if I take the clockwise direction as positive, what do I have? I have plus mb, plus moment at fixity. Concerning the distributed load, it's doing a